Sigmund, you're going to start.
Okay, thanks. So it's a pleasure today to welcome, well, of course, all the speakers and in particular, all the audience, and in particular, our speaker, Andreas Hüttel from the University of Regensburg. Just to briefly introduce Andreas, he studied physics at the Ludwigs-Maximilians University in Munich, where he also did his PhD at the chair of Jörg Kotthaus on quantum dots in 2005. Then he left to Delft for a postdoc working on molecular electronics. And in 2009, he came back to Germany, to Regensburg, to work on carbon devices. And there he also did what Germans typically do at, say, after the postdoc. He went through this habilitation track and received his habilitation, a couple of years ago. Then he was visiting professor in Helsinki, and since this year he's back to Regensburg and worked on carbon nanotubes and quantum devices. And what I should also mention, this year he received the Schottky Prize from the German Physical Society for his achievements in solid-state physics. And another thing is that he's also working for the Linux community, so at least some of us should be grateful to him for his efforts in that direction. And with this, I will announce today's talk. It's about quantum devices in single carbon nanotubes and quantum electronics. So, Andreas, welcome here to our virtual seminar, and please.
Yeah, thank you very much for the invitation. It's really great to be here and to present our work. So, quantum devices and quantum materials, single nanotube mechanics, and quantum electronics. Well, the work in my group is actually going in two different directions at the moment. Let me just very briefly introduce this. So we have a focus on one-dimensional systems, on electronic low-temperature experiments, millikelvin DC to gigahertz. This is one of these so-called DFG Heisenberg grants. We're doing our research at the University of Regensburg. And the two branches are, on the one side, quantum materials, on the other side, quantum devices. On the material side, we are trying to look at something new, namely transition metal dechalcogenide nanotubes. You all know this as 2D materials. But MOS2, for example, also forms tubular macromolecules. And these could be great semiconducting quantum dots. They could also be intrinsic non-central symmetric superconductors, astonishingly. They have, like the planar MOS2, strong spin orbital interaction, and they might have non-trivial topological properties. So there's lots of interesting things to be looked at. And this is a project we are building up at the moment. The other side is quantum devices, and there we continue our work on carbon nanotubes, specifically the microwave optomechanics with these. And this is what I'm going to tell you about today, mainly, because otherwise the 45 minutes just wouldn't by far be enough. So, carbon. This is how everybody knows carbon, diamonds and coal. But of course, we all know by now that carbon has more modifications. We can have fullerenes, we can have graphene, which is basically single layers of graphite. And if you, in a thought experiment, roll up a single plane of graphene, then you get a carbon nanotube, a tubular macromolecule consisting of carbon only. If you look into more details, then you will see, of course, there are different types of nanotubes. You can have single-wall nanotubes, you can have multi-wall nanotubes, and even among the single-wall nanotubes, there are many different types, depending on how precisely you wrap up your graphene sheet. Now, people have been fascinated by these nanotubes for many years now, and there are many different reasons for it. On the one hand, the mechanical properties. They are stiffer than steel, they are very resistant to damage from physical forces, and they are very light. And you can quantify this, for example, with the Young's modulus, much higher than steel. with density as the bulk material, of course, lower than even the lightest metals. So this is a material of engineering dreams, as you can also see from this journal cover already from 1997. But also they make excellent nano-electromechanical systems. On the electronic side, explaining the structure of carbon nanotubes nowadays is pretty easy because everybody knows graphene. So everybody knows these Dirac cones of the dispersion relation of graphene. And if you know, say that as a first approximation for forming a nanotube, you take a graphene sheet and fold it together, wrap it into a tube. Then you can impose periodic boundary conditions onto the dispersion relation of the graphene. You make one-dimensional cuts through this plane, like the yellow lines here. And depending on how you exactly wrap up your sheet, you either hit the Dirac points, then you get a metallic nanotube, or you don't, and then you get a semiconducting carbon nanotube. You have the same two Dirac points as in graphene, two non-equivalent Dirac points, and thus electronic states can have together with the spin a fourfold degeneracy. Yeah, by now carbon nanotubes have reached in many respects already technological applications. And these go in very different directions. If you look at the mechanics, there's a lot of material development, material research. And that goes from military armor all the way to this chic bulletproof suit. So it's very light, but it's actually bulletproof. It also costs $20,000. Or the surfboards here. On the electronic side, well, you can either use them as transistor elements when they are semiconducting, or you could use them as vias, as highly conductive connections between chip elements. And there's also a lot of research going into this. And this is a really outstanding result from 2 years ago, 2019, a Nature article, a modern microprocessor built from complementary carbon nanotube transistors. This is a microprocessor of a complexity that can actually, in principle, run a modern operating system built with carbon nanotube transistors alone. But also, for example, nanotubes are by now an important component of most mobile phone batteries. Yeah, we are looking at single such nanotubes. We are interested in the properties of these at very low temperatures. So after the nanofabrication, here you can see a simple example device where you can see one carbon nanotube lying across a trench between two metallic electrodes. So after the nanofabrication, electron beam lithography here in this picture, we place our devices into a dilution refrigerator. This is still one of the old wet models, and measure conductance, measure currents at low temperature. There is one phenomenon that I should at least briefly introduce. I guess most of you are very, very much familiar with this. That is Coulomb blockade. We have a conductive nano object, our carbon nanotube. And you all know that to charge a capacitor, you need energy. The smaller your object becomes, the smaller the capacitance becomes. That means the larger the energy becomes to charge it with a certain charge. And now if we have such a nano object, if we are at very low temperature, then the thermal energy in the environment might not be enough to charge it with a single electron. And then what occurs is so-called Coulomb blockade. A current through the system is a priori blocked because there is not enough energy available for one electron to enter the system to charge this local system with one elementary charge. Only for very specific values of the electrostatic potential, an electron from the Fermi edge of metallic contacts can enter the system and then can tunnel out onto a free state at the Fermi edge again. And as a function of a gate voltage that tunes this potential, you then get these characteristic Coulomb blockade oscillations of the conductance. In the regions between the conductance peaks, the number of trapped electrons on the nanotube is fixed. On the conductance peaks, it can fluctuate by 1, and current can be carried via single electron tunneling. And when you tune the gate voltage, you charge your system with 1 electron after the other. Now, if you want to do spectroscopy, you can tune one more knob, and that is the source drain voltage, the voltage that is applied across the nanotube. And then these Coulomb oscillations, which correspond to the cut here at 0 source drain voltage. This is the cut here. They expand into finite regions of current. And these regions, they are not featureless. They have steps in the current corresponding to resonances or to lines in the differential conductance. And these lines, they correspond to excited quantum states of the trapped electronic system. And from their positions, for example, we can directly read out the excitation energies. Now, this here is a sketch. This here is a measurement. Here we have actually really the band gap, so 0 electrons in the conduction band. Here we have 1 electron trapped in the system. And the lines that we here see correspond to the ground state and the first excited states of 1 electron trapped here in the conduction band of the nanotube. Now we can, of course, this is most interesting if you look at dependence on additional parameters. So for example, we can now take cuts along such a red line here, 1, 2, 3, 4 lines, 1, 2, 3, 4 lines, and apply a magnetic field parallel to the nanotube. You can see the lines split, they show very distinct dispersion, and that allows us to identify them and fit them, actually with a straightforward single particle Hamiltonian in this case. And we can extract the high-level parameters like the spin-orbit coupling, the valley mixing, and so on. You can see that for this field range here around 1.5 Tesla, we end up with essentially pure spin and valley states. So this is a very well-researched system by now. And we are not the only ones who have made such measurements. But even in such essentially well-known and rather simple system, 1 electron in the band structure, additional corrections are needed to fit this. And there are still many open questions if you look at the details. It gets more interesting if you don't go to 2 Tesla, but to 17 Tesla. Then you can see that you basically apply a flux through the nanotube, and you are shifting your cuts across the Dirac cone. So this is basically tracing the Dirac cone of the graphene. Again, we can apply fits. Again, we can extract the parameters of the dispersion relation. But here, there are even more puzzling things left. For example, one puzzling detail is why are these lines that go up vanishing so quickly? You can see this is basically one valley. This is another one. And here the lines, the conductance immediately disappears. And this was something that we looked at some time ago. So basically there's a special effect due to the bipartite hexagonal lattice of the graphene. You get a non-standard boundary condition, a non-standard quantization condition for the trapped wave functions. You end up with a term that makes a cross-quantization, meaning it couples the longitudinal and the transversal wave function in your trapped system. And you can tune, well, the trapped electron from a lambda half shape, like this here, to something like lambda quarter shapes. And now, of course, the strength of the wave function near the contacts dominates how strong your tunneling goes. So these effects become visible in the overall conductance. If we plug our model into, if you plug this model into a tunneling calculation, then you see that we can reproduce, for example, that these lines here disappear rather nicely. So this just as an example of what you can do in terms of transport spectroscopy on such a system. Now let's switch gears a little bit and switch from the electronics, as I've already announced, to the mechanics. How can you, you've seen that this nanotube is hanging across a trench, so it can vibrate like a string resonator. And how can you show that? Well, in these low temperature experiments, there's actually a very easy way to do that. You hang an antenna on top, just contact free. It's basically just an open-ended coaxial cable. You apply a radio frequency signal, you sweep the frequency, and at some point you get in your DC current measurement a huge spike. And then you can zoom in, you can go to lower signal levels, and at some point you see this is a very, very sharp resonance with a mechanical quality factor of somewhere around 150,000 in that case. This was the first measurement where this was shown. That's already 12 years ago. And in the meantime, people have demonstrated that you can reach mechanical quality factors with carbon nanotubes in the millions, 5 million, 7 million or so. Now, you may say this is just a spike here. How can we prove that this is actually a mechanical resonance? Well, you all know what you can do with mechanical resonances. You can, if you have your piano or if you have your violin, you can tune one of these knobs and change the mechanical tension in the system. And that changes the resonance frequency. And we can do the same thing here. And astonishingly, it's really enough to change the electrostatic forces in the environment to tune the mechanical frequency. We somehow never really got around to publishing this particular graph here, but it's a very nice one. You can see here the mechanical resonance frequency here. It's very faint, but here it gets already stronger. This is the mechanical resonance as function of the gate voltage across the first Coulomb oscillations, from the band gap to 1 electron trapped in the system, to 2 electrons trapped in the system, to 3 electrons trapped in the system. And if you look at an electrostatic model, you end up with 3 effects. One is a slope, one is a step, and one is a dip. The slope corresponds to the continuous charging of the gate electrode. You are increasing the gate voltage. The charge on the gate electrode is increasing in a continuous way, and thereby you are continuously increasing the tension in your system and the mechanical resonance frequency. The steps, they are the discrete charging of the nanotube, of the quantum dot. So at each of these Coulomb oscillations, you add 1 elementary charge, and that adds a discrete amount of pull, a discrete amount of mechanical tension, and thereby resonance frequency. And the dips, finally, they correspond to so-called electrostatic softening of the resonator. It's much easier, actually, to explain this in words than in formulas. Here, the charge on the nanotube can change. So this is the region where the system can adapt in charge. And that means that during one oscillation cycle of the mechanics, when the nanotube comes closer to the gate, the charge can adapt a bit. When the nanotube goes further away from the gate, charge can adapt a little bit. And that leads to an additional force term that counteracts the mechanical restoring force, a negative spring constant contribution, and that leads exactly to this drop in resonance frequency. You can write it down, and it's effectively proportional to this derivative here, the derivative of the time average charge by gate voltage times gate capacitance, geometric gate capacitance. And in a way, if you can imagine, if you integrate this over Vg, this area here somehow corresponds to this one single elementary charge that is added to the system. Also, this you can use to do nice physics. For example, we can look at the resonance evolution in the Kondo region. Not going to explain in detail now what the Kondo effect is. I am either it would take too long or you already know it. So we are at higher conductance now. We go from even to odd, from even to odd occupation of the quantum dot. And the Kondo effect is a hybridization effect that leads to an additional conductance via higher order tunneling when there is an unpaired spin. So when you are at odd occupation. And now we can look at how the mechanical resonance evolves there. And we can extract the resonance positions, we can extract the resonance frequencies. And as you can see, there is already like an obvious difference between the upper and the lower curve. The upper one has this odd-even imbalance. So you get a Kondo effect for odd electrons number, you get a Coulomb blockade for even electrons. But down here in the resonance frequency evolution, there is no such odd-even effect. And it turns out the mechanical resonance is acting here as a charge sensor and provides a quite nice experimental proof that the Kondo conductance is carried only via virtual occupation of your system. Okay, this is a simplified picture, but I think it still captures the essence of what happens quite nicely. The electrons, when the Kondo effect carries the current here, the electrons hop in and hop out so quickly that they don't contribute to the mechanical effects at all. It's also consistent with the resonant tunneling picture, because if you look at Friedel's sum rule, then a constant perfect transmission, as you expected for Kondo effect, implies a constant time average charge in here. So apart from the higher order processes, this is not so much different from the Coulomb blockade area. Again, if you're interested, this is the paper. So this is a very nice example of what you can do with well, this mechanical resonance detection. Okay, now we have a problem. Why do we have a problem? Well, what we actually want to do is mechanics in the quantum limit. And our nanotube is a very nice mechanical system for that. We have a resonance frequency somewhere around 100 megahertz. We have temperatures in the cryostat of somewhere around 10 millikelvin. So if we calculate the thermal occupation, we end up with 2, and that's great as a starting point. The problem is that for our mechanical resonance detection that I've shown so far, we need to drive our vibration. And that destroys this nice number, because we drive the vibration. We can estimate from the signal levels the amplitude of our mechanical resonator, and then we end up somewhere around n is 1000 at least. So that's quite far from the quantum limit. If we really want to do quantum mechanics, we need to try a different approach. Yeah, and for doing something in that direction, we looked then at our colleagues from optomechanics. You probably have heard of optomechanics. It's a highly active field of research where the coupling between mechanically oscillating systems and cavities for light or microwaves are studied. And as you can see here from this picture, from a review that is already 6 years old again, this has been studied in many different material systems and many different types of devices, ranging from the gram or even above, suspended macroscopic mirrors, all the way to cold atoms coupled to an optical cavities, so in the septogram range. All these systems essentially have the same physics in common. And the prototypical optomechanical system is a cavity with a moving mirror. So we have a laser cavity, and one of the mirrors here is mounted on a beam that can mechanically vibrate. Now we have another problem, because let's just say for our trapped electrons in the electrostatically defined potentials, optical frequencies are high energy physics. So if we shine onto such a device with a laser, we end up making excitons, we end up with interband transitions, and that's something that we don't want. So optical frequencies are kind of out of the range that we want to use. But luckily, there's an alternative to that. There's also the so-called field of microwave optomechanics. And it turns out this system here, the laser cavity with the mirror on an oscillating beam, is 100% equivalent to this system here, a microwave cavity, an LC circuit, with a capacitor where one of the plates can vibrate. Both are described by the same interaction Hamiltonian and by the same main coupling constant, this G0, the zero photon optomechanical coupling strength, that describes how much your cavity frequency changes if you shift the mirror by the characteristic length scale of the mechanical harmonic oscillator. And you can also write this down in terms of the capacitance, and then you end up with a similar expression here. So this is more or less the experiment that we should have to make, because if we can build up a system like this with a carbon nanotube, then we can use all the formalisms that the experts from optomechanics have developed and all the experiments and techniques from there, and manipulate and cool and prepare our mechanical quantum system. More precisely, what we should probably do is build an experiment like this. This is one of the early optomechanics experiments where you have an aluminum beam coupled to a superconducting coplanar resonator. You have these worm-like structures. They are the coplanar resonators for the microwave. And the beam here can vibrate. It changes the capacitance between the inner conductor and the ground plane, and thereby provides just the interaction that I've mentioned. So if we can build something like this with a carbon nanotube, then we can detect and manipulate the motion without strong driving. I mentioned this is a very well-researched area, so the theory also exists, and we can insert the numbers for a carbon nanotube. And the carbon nanotube is in some respects really great. You can see here the high resonance frequency and also the large 0-point fluctuations of the position, because it's very light. But on the other hand, if we look at the coupling parameters between such a microwave resonator and a suspended carbon nanotube, well, the numbers are abysmal. They are tiny. And that's basically because a single bar carbon nanotube is a great mechanical resonator, but it's also annoyingly small. What we have here is a mismatch of scales. The microwave resonator, the length is given essentially via the resonance frequency and the wavelength. And there we end up with a scale of 1 centimeter. If we want to have a nanotube that traps single electrons in well-defined quantum states, we are in the length scale of 1 micron. And if we look at the vibration, then the typical deflection is on the order of 1 picometer. And you can imagine that a deflection of 1 picometer is not influencing a 1 centimeter large system that much. So that's basically the reason for the red numbers here. Anyway, we built it anyway because we knew better. And here you can see our chip. So we have a coplanar waveguide resonator. That's this snake-like line here with an input coupling capacitance, with an output coupling capacitance. In the middle, we can apply a DC bias to the center conductor. And in these two regions on the left side and on the right side, we can insert a nanotube into our chip. How does this work? Well, let's zoom in. Down here, we have again the center conductor of the coplanar microwave resonator. And that has a voltage antinode here. So this is the region where the voltage is oscillating strongly. And here it's connected to a gate electrode, a gate finger, that passes here below and goes up all the way. You can't see it anymore because it becomes too narrow. The transparent rectangle is a gate isolation layer, and on top of that, we have 4 contact electrodes for our nanotubes. On the left side, on the right side, there are 2 deep-edged areas, 2 holes, which allow us to deposit the carbon nanotube. How do we do that? Well, we grow our nanotubes on tuning forks. These are exactly the tuning forks that we know all from quartz watches. It's just one piece out of a quartz crystal. We remove the metal, we put catalyst on top, then we grow nanotubes. And you can see they grow in a very straight fashion, and they cross the gap here between the 2 tines. And then we can take our tuning fork, we can lower it down onto the electrodes, and at some point we touch the electrodes and we get electrical contact. And then we can apply a large voltage between contacts 1 and 2, and a large voltage between contacts 3 and 4, and burn away the nanotube there, like this here. We can retract the fork, and then we have our nanotube crossing the center gap between electrodes 2 and 3. And the very nice thing about this is a process that can be repeated. We can build our superconducting circuit, and then we can transfer in a nanotube. And if we're not happy with the nanotube, we can just burn it away and put in the next one. So that makes life in some ways much easier. Yeah, and now we have to show optomechanical coupling. And we went to the experts there, and okay, first it goes into the cryostat. I mean, for those who do experimental low temperature physics, this should be fairly standard. We have the high frequency cables that are cooled via attenuators on the input side. There's our device here, then the circulator, a low temperature amplifier, room temperature amplifiers, and the whole thing is characterized with a network analyzer. And of course, we have additional DC voltage sources and additional microwave sources when needed. Now, we asked what type of experiment should we do to unambiguously prove that there is an optomechanical interaction. And the advice that we got was we should do optomechanically induced transparency. What's that? Well, we apply 2 microwave tones. We apply a strong drive tone, and that is redly tuned from the cavity frequency by the mechanical frequency. And then we apply a weak probe tone that is swept across the cavity of the microwave resonator. Now you all know if you apply 2 AC signals to one object, then you get sum and difference frequencies. And that means if the distance between the drive and the probe is exactly the mechanical resonance frequency, then we get a beat at the mechanical resonance frequency, and that beat drives our mechanics. And that means energy gets lost, so we get a decrease in transmission of the probe tone. So we should see a small dip when this precise resonance condition is achieved. Can we see that? Amazingly, we can it. The large line here is the cavity resonance, and this tiny dip here is the coupling with the mechanics. This is our mechanical resonance of the carbon nanotube. And we can fit this and obtain a coupling parameter of 100 Hertz. And that is 10 to the power of 4 larger at the 10 millihertz that we obtained with the simple theory estimate. If we had really here 10 millihertz, we wouldn't see anything. We would just see the big cavity resonance, nothing else. So obviously in this theory from the aluminum beam, something important is missing. We kind of have skipped an important detail, namely that the carbon nanotube is a quantum dot. It's a Coulomb blockade system. So maybe let's vary the gate voltage as additional parameter and see what happens. So let's take traces like this, and in addition, vary the gate voltage. And this picture is what you get then. Here on the x-axis, we have the gate voltage. On the y-axis, we have the frequency of the probe signal. And each cut like this here corresponds to a trace like this here. And you can see that when we go across one Coulomb oscillation, we have an increasingly strong dip at the flank of the Coulomb blockade oscillation. At the center of the Coulomb oscillation, it shrinks back to nothing again. And on the other side, it comes up again and then disappears into Coulomb blockade. The deposition, so where it exactly is, that corresponds to the mechanical resonance frequency. That's not so interesting. But the dip depth, so the signal strength of this dip here, that corresponds to the optomechanical coupling. And so we can take a fit for each trace here and extract these coupling parameters. And you can see how it increases on the flank and then goes to 0, increases on the flank and then goes to 0 again, and reaches values up to nearly 100 hertz here. What's happening? Well, the nanotube is not a metallic beam, but it's a Coulomb blockade system. And we've been going at this the wrong way. We've been looking at the geometric capacitance that changes when you move the nanotube. But in the end, what we need to look at is the quantum capacitance, the capacitance that is seen by the coplanar resonator. So how much the gate capacitance here, how much the gate charge here changes as a function of gate voltage. And then we also have to take into account that the nanotube moves. And that means not just that the geometric capacitance changes, but it also means that the Coulomb oscillations shift. And so if we are just at the right working point, we can influence the system much more by a small motion than just by the geometric change of the capacitance alone. We can calculate this effective capacitance, and we get an amplification factor compared to the change of geometric capacitance. If we pick the working point right, we end up with a 10 to the power of 4 here. And that's just the factor that has been missing. We can plug numbers into this model. So here we have one Coulomb oscillation modeled as tunneling through a Lorentz-broadened level. We insert our device values, and we get really a nice agreement of the evolution of the optomechanical coupling parameter with this theory curve. And even the absolute values fit rather well, given the many assumptions that went into the model. Yeah, and now this suddenly becomes much more interesting. Why does it become much more interesting? Well, first, let's look at this table here again. We filled in the new values, and now our coupling is much stronger than even for the aluminum beam. Zero photon coupling, dispersive coupling, the sideband cooling rate, and there's a lot more of these characteristic numbers for optomechanical systems, and they are all rather large. And this is much more interesting because now we are reaching parameter regions where interesting physics happens. We can look at, for example, strong optomechanical coupling, hopefully in the future. What does that mean? That means hybridization of the mechanical and the radiation mode. You get basically an anti-crossing of the two. That means that the coupling is larger than the line width. we can insert the numbers, and we are clearly not there yet. We need a stronger drive and a better cavity Q, but it's not unrealistic for future improvements, and we are already working on it. The other interesting point is the quantum coherent limit. That's the situation where you can move an energy quantum from the mechanical system to the electronic system and back faster than thermal decoherence occurs. And again, we can insert our numbers, find that we are not there yet. We need a stronger drive and a better mechanical quality factor. But again, this is not unrealistic for future improvements. And of course, there's also a different side to it. This was now purely from the, well, viewpoint of optomechanics. But there's also a quantum transport side. We now have the interplay between the motion and transport through single well-defined quantum levels. So in future experiments, we can, for example, look at the energy balance between the vibration and the single electron tunneling current. We could try to detect and characterize the cooling or the heating of a vibration mode by a current. And there's many possible extensions to that. For example, looking at the impact of spin polarization, ferromagnetic contacts, or Andreas phenomena, superconductors. And of course, while this here is all steady state experiments, one could also go to time domain experiments. You can look at quantum manipulation. We have a switchable and strong coupling, so we could apply pulse voltages and microwave signals. And also try, for example, not to look at a continuous current passing through the system, but at the dipole of a single electron trapped in a double potential well, in a double quantum dot. Should be possible to do a similar amplification effect there. And then we keep the electron, so we can hope that our electronic system also remains coherent, and that we can do a coherent coupling with this effectively charged qubit. And if you look at recent papers, there has been a very interesting theory proposal from Adrian Barthold, Fabio Pistolesi, and Andrew Cleland, where they propose to build a nano electromechanical qubit in a very similar way. So essentially, there are exciting times ahead and also a lot of work, of course. Yeah, and with that, I'm slowly coming to the end. I would like to thank, especially, of course, the students, my group members, who have been involved in the work that I've shown here, but also all our collaborators. Speaking of students and collaborators, I have to mention we have an open PhD position on exactly this project, microwave optomechanics of the transversal carbon nanotube vibration. So if you're interested, or if you know someone who might be interested, give me a shout. Available now to be filled soonest, and here's also a link. And with that, I'm really at the end and would like to thank you for your attention and would like to ask for questions.
Okay, thank you, Andreas, for this very interesting insight to this fascinating field. So I'm sure there are quite a few questions. So if anybody would like to start, just unmute yourself or write to the chat. One question that I had in the very beginning was, you showed these lines in the transport spectroscopy of the excited states.
Yes.
What is their nature? Is this the angular momentum for rotating around the axis of the nanotube?
Yes. Yes.
Okay.
So basically, here, I mean, in this case here, you have basically two shells with two Kramers doublets each. And if you apply a magnetic field in parallel, you basically split up the you get basically interaction with the orbital magnetic moment and with the Zeeman effect, and you end up here with angular momentum eigenstates and spin eigenstates. At low field, it's more complicated, obviously, because of the spin-orbit coupling and the valley mixing. But here you have the angular momentum and spin eigenstates. But of course, this is the one electron case. It gets already much more complicated if you have two electrons. And same as here, basically, you have, for the lines that go up here, you have the one angular momentum direction, and for these lines that go down here, you have the other one.
Okay.
Maybe I can ask a question, Andreas. Very nice talk. Thank you very much. So I have a question related to these results you showed for the Kondo effect, where you compare transport with the magnetic resonance.
Yes.
Sorry, the mechanical resonance there. So yeah, of course, as you mentioned, when you are writing the Kondo limit, you have complete decoupling between spin fluctuations and charge fluctuations, and this is why you don't see anything in the mechanical resonance. But my question is about moving out of the half filling in your pure Kondo limit when you start to have mixed valence fluctuations still in the Kondo regime. Can you see this in your mechanical response somehow?
We haven't looked at it in this regime. So sorry. And we basically we focused on this one parameter area. What we did was we increased the temperature, and then you see how the Kondo effect becomes lost and how you can basically still trace the mechanical oscillations. You basically reduce the impact of the higher order tunneling processes step by step. But I'm not sure if this is what you're looking for. So.
Well, yes, as you move outside the Coulomb Valley, the middle of the Coulomb Valley, you should start to see some valence fluctuations that in principle contribute to Kondo effect still, but in which
could be done, but we haven't done it in this detail now.
And maybe a related question is, how about SU4 Kondo physics in these kind of devices? Do you see any feature there? Again,
in this particular device, in this regime, we mostly saw, this was mostly dominated by SU2 behavior. If there was any SU4 Kondo effect here, then it was at most a small perturbation. Could be studied in principle. I see no problems with that, but we haven't done it yet.
Okay, thank you. I think there are more questions.
Do you see
Sigmund? Yes.
Raised hands?
Yes, Walter Arnold has a question.
Oh, yeah.
Let me unmute you and you can ask the question yourself.
Okay, now can you hear me?
Yes.
Okay, thank you for the interesting presentation. What determines the damping of the carbon nanotube?
Mostly the electronics. So it's basically the electronic tunneling in and out. The simplest model that you can imagine is that you basically have a retardation if you, let me just find this. Yeah, basically the motion does the same as a gate voltage. It shifts up this level here, up and down a little bit. And you can imagine now that it's moving down, an electron goes in, it's moving up, the electron moves out again. But of course, if there's a retardation, then this involves adding energy to the electron. And that energy comes from the mechanical mode. So that's kind of the simplest picture that you can imagine.
Is there any contribution from phonons?
What do you mean by phonons? Do you mean the vibrations? I mean, you could say vibrons, or do you mean the crystal, the bulk crystal around it?
The bulk crystal around it.
That's an interesting question, and I don't know. I think the electronic effects are much stronger.
Okay. Thank you.
Sigmund, there is another question by Ferry Prince.
Yeah. Hi, Andreas. Very nice to see you.
Nice to see you.
Very nice talk. I have a question about your fabrication. I think it's very elegant what you do with your tuning fork. How does it compare to the old-fashioned way, where you have kind of like these ultra clean carbon nanotube grows and it falls on top of the electrodes? How do the Q factors compare? Are they as good as the old ones? Are they maybe even better?
We don't really have enough statistics yet to say that. I mean, the problem is the problem with the old fabrication is a very technical one, and it cost us a couple of years because I mean, our first approach to this experiment was to basically make the chip and then grow the nanotube in situ.
Yeah.
And it turns out this is, well, theoretically possible, and in practice has a yield of 0 because the high temperature growth process for the carbon nanotubes eventually destroys every superconducting resonator.
Yeah.
So you can use the in situ growth and these ultra clean tubes for simple experiments, but it's impossible to do it with a complex chip. Just imagine you do like a really complicated chip preparation, and then your last fabrication step is one that likely destroys it.
Yeah, yeah.
And I mean, the big advantage of this technique is that we can insert the tube, and if it doesn't work, we can insert it again. The difficulty is a little bit, I mean, that you don't just get single nanotubes here, you also get bundles. But on the other hand, a priori, I see no reason why these should be dirtier than the other ones, because it's more or less the same process.
Yeah.
We use a different catalyst a little bit. We use cobalt instead of the nanoparticles that we used in Delft and also later used in Regensburg. But apart from that, it's the same gases.
All right, thanks.
Alfredo.
Yes, hello, Andreas.
Hello.
Thank you for the presentation, and sorry that I could not attend the full talk, but I wanted to ask, you have increased the coupling a lot, no? So why don't you see replicas of this signal? So multi-phonon processes. Is this possible?
Because I think we are not in the, because I think our resonance is still too wide for that.
Mm-hmm.
We need higher mechanical Q factor, and we might also need a higher optic Q factor. So I think we just don't have the resolution for that yet.
What was your Q factor of resonator?
Oh no! Wait! Sorry, now I got confused. You mean multi? I don't know. Maybe we just didn't look at it because this would be like 500 megahertz off, and we ended up with this device with a much higher. Mechanical resonance frequency that we actually originally planned for. And our mechanics was at 500 megahertz. And that made the experiment in part a little bit challenging because the sum difference frequencies were always so far off in this case.
Mm-hmm. Mm-hmm.
So it's possible that we just didn't look at it, yes.
Okay. But for curiosity, what was your Q factor of the resonator? Because I was not listening the whole talk.
For the mechanical system, I think somewhere around, I don't know exactly anymore, but maybe somewhere around 20 to 50,000.
20 to 50,000. Okay. And the photonic?
Low, 500.
500.
That was a fabrication defect.
Oh, this can be made much higher, no?
Yeah, we made resonator chips without these carbon nanotube transfer areas that had a microwave cavity Q of 200,000 or so. But the limitation is not so much the nanotube itself, but that let me show you, that these coupling electrodes here, of course, also couple energy out of the microwave resonator. And at the moment, we've been working a lot with Sonnet to optimize this so that we don't lose so much of the microwave signal over the DC lines.
Okay. Thank you, Andrea. Thank you.
Okay, I see no further question. So, well, if there's no further question, let's close the session and thank Andreas again.
Thank you.
And so we stop the YouTube recording, and those who want to stay and chat a little with Andreas are welcome to
Sure.
stay.